Welcome. This recording is an illustration of how to use R to fit a GLM. We will use the dataset that was discussed in the lecture, and the first step is to look at the data and understand how it's organized and what kind of data we have. So this is the CSV file with the data, and you have one main response. It's the average of the claim amounts for different categories or different groups. You also have the number of claims that were observed in that particular group. And a group can be, specified by four factors. The first factor, by three factors, sorry. The first factor is the policyholder age, and this can be from 17 to 60 plus. So there are 8 categories. The two first columns basically give the same information. In the first column you just have a number from 1 to 8, and in the second column it says to what age group it corresponds. Then the second factor is the car type, and here you have 4 different ones: A, B, C, and D. And the third is the age of the vehicle. You have 4 categories: 0 to 3 years, 4 to 9 years, 4 to 7 years, sorry, 8 to 9 years, and 10 and plus years. In the same way as we have done for the first factor, we have numbered these categories 1 to 4. What's interesting to note here also is that you have a certain number of claims. If you look at the sum, you have a sum of 8,942 claims for 128 different categories. So constellation of these 3 factors. And in some cases, like here, and in 2 other places, there is no observation. So we have no observation, no claim for policyholders between 17 and 20, car group C, and vehicles of more than 10 years. So what I want to show you now is how you can fit a GLM to that data. So I have prepared the code in advance, and I'll just comment the code and the outputs. You have in attachment to this recording the R code and the dataset, so you can run it yourself afterwards. So the first thing you need to do is to load the data. So we will read this CSV file and put it somewhere, and we'll take in to fit the GLM, we'll remove the 3, actually it was 5 categories that have no claims. So we take this big table from the CSV, and we put in pcar_ins the elements of the table where the number of claims is more than 0. Okay, then we can summarize the data. You get some data about the average claims. The median is lower than the mean, so you have a skewed distribution, and so on. Of course, the summary for the factors don't really make sense. What is more important is for the average claims. We will fit the GLM based on 3 different factors. So you have the policy age, the car group, and the vehicle age. So you need to tell R that these are the factors, and you do that by saying, okay, the factor policy age is what you have in the column pol age of the table pcar_ins, and you have to consider that as a factor. So we do that for the 3 factors, and then we are ready to fit the GLM. So as a first approach, and that's the one we have in the lecture, we will do a GLM with the 3 factors and possible interaction between these factors. So I'm going to put my GLM in in an object that I call model 1. So model 1 is a GLM where the column average claims in the table pcar inch is explained, so that's what the mains tilde, but what the sign tilde means, by the policyholder age, so that was the factor we have defined here, the car group, the vehicle age, and then you have the interaction between the policyholder age and the car group, the policyholder age and the vehicle age, and the car group with the vehicle age. And then we put weights to these observations. Remember, we have 128 minus the 5 where we had no observation, so we have 123 observations, but for each of these observations you have a varying number of weights. So you can take the weights as the number of claims. If you had 200 claims, obviously you should give more credibility to that observation than if you have only one claim. So that's what this does. And then here we make the assumption that it's gamma. So the family of the exponential dispersion here, we say we want a gamma 1. So when you run this, nothing happens. Well, you're just sending the GLM in model 1. So what you want is then what you can do with that is you can ask for a summary of the GLM. So this summary will recap what you're doing. So that's your linear model here, and then gives you some stats about your deviance residuals, and we see that the median is about 0, and you have a minimum of -2 and maximum of 1.8. This gives you an idea of the range of the residuals. So it seems to be more or less symmetrical, and with most of the residuals, we have 50% of the residuals between -5 and 0.4 overall. Then you have a table with all the coefficients that have been estimated by the GLM. So the GLM is you have a linear model. Remember, it's beta times x. So you need here, and the policyholder age, for instance, you have 8 categories. So what the model will do is that they will put the age 1, the first, in the constant, the intercept, and then you will have one parameter for each of the other categories, which means that if you are in category 3, then you will have the intercept plus the coefficient for category 3, this one, times 1. So you have the estimates of these parameters here, and then you have standard errors for these parameters. You have a lot of parameters here because you had the 3 factors and then all the interactions. The standard errors, and you have a test to see if these things are significant. So interestingly here we have so many parameters that the only one that's really significant is the intercept. You can find 2 other ones that are more or less significant, but what this table tells you, well, this table doesn't tell you much, but you can say that since none of these are significant, you have probably too many parameters. So then R tells you what the dispersion parameter has been used. So for the gamma you have something different from 1. This makes sense. If you look at your lecture notes, you'll see that the dispersion parameter for gamma family is not necessarily 1. So, but here it just gives it to you for your information. Then you have 2 information here, 2 deviances. The first one is the null deviance. That's the deviance you would have if you had only one intercept in the model. The intercept would be the overall mean. In that case, you have 123 observations minus 1 degree of freedom, so you have 222 degrees of freedom. Then you have the residual deviance, so that's the deviance that's left after you have applied the model. And here you see you have 65 for 58 degrees of freedom. And this gives you also the AKK information criterion. I remind you that you need this should be as small as possible. Then you have the number of Fisher scoring iterations. This is just an information about the estimation of the parameters. Of course, you need to use numerical methods to estimate all the parameters, and this tells you how many iterations the R has needed to come up with these estimations. So you shouldn't really worry about that unless it's very high. If you have, I don't know, 224 there, it means that the program needed a lot of iterations to estimate the parameters, and probably it means that the program is too complicated and you should not put too much confidence on the estimation of the parameters. Then you can do another thing to that GLM is to look at the ANOVA analysis. So this is an analysis of the deviance table. That's what we did in the lecture. It just recaps that you are in a gamma model, so the link is it's a reciprocal link, and the response is the average claim sizes. So you have this table here, which is the same as the one we have seen in the lecture. So you have the overall mean, and then you add in the sequence all these factors. And with the rule of thumb, we were looking at the what you were gaining in terms of deviance, and comparing that with the double of the degrees of freedom you have lost. So remember, with the rule of thumb, we had stopped here at the third line because 2 times 34 was more than 2 times 21 was more than 34. So with the rule of thumb, we should use the 3 factors but no interaction ones. Here you have the same kind of approach but without the rule of thumb. So you have a chi-square test, which was what we were using, and we were using the rule of thumb saying we will stop when this probability is more than 5%. But here you have the actual calculations for these probabilities, and you see that the 3 first one are significant, and here you have 8%. It's more than 5%, but it's close. It depends what level you want to use. If you wanted to use a 10% significant level, maybe you would like to still to keep this first interaction one, the policy older age and the car group. It would make sense with the example I used in the lecture. Say if you have a very young driver with a Ferrari, it kind of makes sense to say that you have higher risk than with an old policyholder and the same Ferrari. Maybe not, but here you could discuss on that. On the 2 next ones, you are really here what you gain is really not enough for it to make sense. Another thing you can do that is a bit similar to determine if your factors, if your model is parsimonious enough, is the drop1 function. The drop1 function will check what happens if you drop one of the elements of your model. And if you apply it here, so R says, okay, you can drop policyholder age and times car group, and well, these 3 things here, these are the ones we are really considering. And it says, so you have none, that's the model, the original model. And then if you drop in the model the first one, then you increase the deviance by 101. So 66 is the residual deviance of your model. You can check it up here. That's the 66 you had here. So if you wanted to drop policyholder times car group, you would increase the deviance by 100%, by 100, and this would make an AIC of this. And the scaled deviance, yeah, well, this is more important. That's to know if you drop that, do you have a significant change in your model? And here it's none of them. And also the AIC, I remind you that you want to minimize it. So you see that if you drop each of these, you will improve the AIC. So this suggests also that you should drop the three of them. So here you have the second model. It's exactly the same as before, but I kept only the three main factors. So we can go directly to the summary. I have added something there. I want a table of the correlations between the parameters. I'll get back to it in a moment. So you have again information about the deviance residuals. They are a bit more spread, which makes sense because you have decreased the number of the complexity of the model. And then you have a smaller table with the parameters and significance levels. So it seems that the vehicle age is always very significant. Now, if you look at the car group, remember we had four categories: A, B, C, and D. A is hidden in the intercept. So the difference between B and A is not very significant. The difference between C and A is significant, and the difference between D and A is significant. So this may suggest that as a further step, you could merge groups A and B and just have three groups: A, B, C, and D. Then you can do the same for the policyholder ages. The policyholder age 1 is hidden in the intercept. And the difference between this one and the category 2, 3, and 4 don't seem to be significant, especially the first one. So whether you are between 17 and 20 or between 21 and 40 and 24 doesn't really change much the outputs. So, but if you move from 17 to 20 years old to the fifth category, then you have a significant difference. So here it suggests that you may want to merge at least categories 1 and 2. You see here it's really not significant, the difference. Here it increases with age, and it makes sense. You would need to try, but you could maybe merge the first four categories and keep the other ones here. This would require some tests to see what happens. So, but these significance levels you can really play with them and try to have a model that is as lean as possible by merging different categories whose difference are not significant. So we have a residual deviance of 124 for many more degrees of freedom. We had 66 for 58, and here we have 124 for 109, and we have an AIC of 84,000 in that model. We needed two less iterations. The correlations for the coefficients. Here's how you can use that table. So you have a triangle here. This is just the end of the triangle that should be there, but I don't have a screen big enough to put everything there. The correlation between the intercept and the factors don't tell you much. It's basically, it gives you information about how much observations you had in the categories that ended up in the intercept. Then also you have the policyholder ages. So if you look at this triangle there, Within this category, you have high correlations, and it makes sense because they are all the factors of the same kind. What is important, what is interesting, sorry, is to look at the correlation of what are not policyholder ages with policyholder ages, so this square there. These correlations, if they are close to zero, they mean that if you they mean that they really explain different things. If you had correlations of very close to 1, it would probably mean that some of these factors are redundant. Then you have car group against car group. These are these ones here. They are high again, but you are in car group, within the car groups. But car groups with vehicle age, it's close to 0, and vehicle age with vehicle age, it's relatively close to 0 too. So this gives you some information about these correlation factors, these parameters. Sorry. So you can get the same table analysis of deviance, and you see again that you should really use the model with the 3 of them here. With the rule of thumb, you stop there. And if you look at the drop one approach, you are increasing the AIC by removing any of these factors. So you should really keep your model. It's probably the best model here without combining categories. Probably the next step would really to try to combine categories to have only significant parameters here. Okay, then you can analyze the residuals. There's a function called fitted, where you can actually you have a table here with 123 observations, and you could be interested to know, well, what does the model yield for these 123 observations? So what we'll do here is that we will the plots here, we will compare the observations with the predictions, and then also compare the residuals of the residuals against the fitted values. So yeah, I should go really from here. So you have your fitted values. We'll put them in vector GLM fit. Then there are functions to get the residuals. This will give you vectors. So the residuals of our GLM model 2, you can get the deviance residuals or the Pearson residuals. What is interesting here is that you can estimate psi hat with the formula we've seen in the lecture. So this is the sum of the Pearson residuals squared. So here you have the vector of the Pearson residuals the Pearson residuals. Then if you square that vector, this gives you a vector of the squared, and you can take the sum of these, and then you divide by the degrees of freedom of the model that you can find here. And this gives you the estimated value of psi according to the formula we've seen in the lecture. And we can compare this with what the model yielded. And the model yielded 2090-81, and you have 2019-48. So you see it's the same. It's really how you estimate the dispersion parameter. So then for the plots you have well, I just showed you the plots. You have observed against predicted, so the observed amount, the fitted values, And of course they should be the same, so they should be on that line with intercept 0 and slope 1. Well, you have some outliers, but more or less it's alright. And then you can also plot the residuals against the fitted values. And what you're looking here is that these residuals should be really around 0, and you shouldn't see a trend. If you had a trend with a lot of residuals here and coming down there, you probably have a problem with your model, because then the residuals are tilted up for lower value and tilted down for higher values. But here you don't see a trend, or you don't see a systematic trend in these residuals, so it looks more or less alright. So these are just this is just the code to get the plots. The last thing that is interesting is that we had 5 missing observations. For 5 combinations of the factors, we had no observations. So in practice, how would you calculate the premium or estimate the losses for these categories? You can't, you have no data. And the good thing with GLM is that you can predict or estimate these values based on the GLM. So that's what we do at the end here. So we create a new table with the data, but here we take from pcar inst temporary. Remember, that was what we had at the beginning. We had read the CSV and put that in the table .tmp, and we had taken only the lines or the rows where the claims were positive, where there were claims. Here we just do exactly the contrary. We take only the lines where the claims are null. And here, so we have defined the factors here from this this table where we had claims of 0, and we will predict what model 2 yields for these factors. So you need to tell the function predict GLM for what values or for what cases of the factors you want the predictions. So that's what you do in the data frame here. You tell R that for the policy age you should take the policy age pred, so the ones we've put here, and these will only be five cases with the following car groups and the following vehicle age. Then I'm just organizing the information. So you get the predictions. These things, this predict GLM gives you a vector of the predictions and the standard error and a couple of other information. What I want is only the fitted, the predictions and their standard error. Also, I want to have a table that recaps what were the policy age cases, the car groups, and the vehicle age. So I've just put in a data frame the policy age, the car group, vehicle age, and then in the column fitted, I take the predict NR, the fitted values, and the S of fit. So predict NR, it's the object we've just calculated there. And as I told you, this function gives you fitted values, standard error, and so on. And so these different things it gives have names. So the fitted values have name fit. So if you put predict.nr $fit, this gives you the vector of the fitted values, and the $s of fit gives you the standard errors. So, and then the table is the following one. So you have the fitted values there according to our GLM, their standard errors, and this corresponds to these factors. So you see we had a lot of young drivers and a lot of category D, and especially for old cars. So these were the cases where we didn't have any observation. But now we are in a position, according to the GLM, to have some estimation of the cost that would occur. That's the end of my illustration of how to fit GLM using R. So we've used the data set that was used in the lecture, so you can reproduce the results discussed.